All right, hi guys, here is 4.2. The title of 4.2 is trig functions. So obviously, you can already tell everything in chapter 4 is going to be trig functions, but this one is specifically evaluating trig functions. So you can see up here at the top, I have a whole little kind of diagram. This, not exactly a diagram, but a list of helpful things when we're talking about trig functions. So this is going to be incredibly important for you to have kind of handy at all times, something that you will want to either memorize or have written down somewhere for quick access. So what this is basically saying is that when we're evaluating for a sine function, that is going to be a y value of a coordinate, which we already kind of know from making the unit circle. When we typically have an xy coordinate, right, instead of xy, in trig, we have cosine and sine of theta, okay? So that is to say that x and cosine are matched up, okay? And then also sine and y are matched up. How this follows for the rest of the trig functions is when we're taking a tangent function, that would be sine over cosine, which given the fact that sine equals y and cosine equals x, it will be y over x. So down below are our inverse functions. So inverse function basically is the reciprocal. So taking the reciprocal of 1 over sine would be 1 over y. For secant, that's the reciprocal of cosine, so it's 1 over x. For cotangent, it's the reciprocal of tangent, so we flipped this fraction to get x over y. Of course, anytime that you are dealing with a fraction, that denominator should not be equal to 0. If it were, it would be an undefined function. So x can't equal 0, y, and x and y in these instances are not allowed to equal 0. So we're going to first start off with evaluating some trig functions. When we evaluate for all 6 of these functions. So we will be evaluating first for t equals pi over 6. So I've done the liberty for you of going to a unit circle and finding out that at pi over 6, the coordinates are root 3 over 2, 1/2. Okay, and again, this was just found by going to a unit circle and finding those coordinates at that location. Let me see. Yeah, I have one right here. I can kind of show you. Where can you see? Okay, right here. So this is my 30 degrees, my pi over 6 dividing line, and those coordinates are root 3 over 2, 1/2. So again, when we're thinking about the fact that this is a coordinate, this would be our x and then our y, or sine cosine, or sorry, cosine sine. Said it backwards that time. xy or cosine sine. So the easiest ones by far would be our sine and cosine. So my sine value from before, I have been told already, is y. So I take the y coordinate, which is 1/2, and I say, yeah, I know that sine of pi over 6 is my y coordinate, which just equals positive 1/2. And that's it for that one. Okay, when we move on to cosine, we know, yep, that's x. My x value is root 3 over 2. So yeah, this value is root 3 over 2. Pretty simple stuff. Tangent is y over x. So I take my y value and then I take my x value over each other. Okay, so I'm going to do the work down here because it's going to have to end up actually having some work done to it. So when we take 1/2, all divided by root 3 over 2, right? Because we take sine over cosine, or our y over our x. When we divide by a fraction, think about that, what that means, and how we can simplify this. So dividing by a fraction is the same thing as multiplying by its reciprocal. So You take your first number, that stays the same. 1/2, what was in our numerator stays there. So now we take our denominator, okay, that whole denominator is √3/2. And we have to multiply by the reciprocal of this. Reciprocal means a flipped fraction. So 2 will be in our numerator, √3 will be in our denominator. 2 in numerator, √3 in our denominator, okay? When we multiply fractions, we multiply straight across. So we have 1 times 2, which is 2, and 2 times √3, which is just 2√3. Okay, in here though, 2 and 2 cancel to be 1/√3. Hopefully by now you've gotten a hint that we cannot leave any kind of square root or root in general in our denominator. To get rid of it, you do that process that's called rationalizing the denominator. Essentially, you multiply by a funny looking 1. That funny looking 1 is made up of the denominator over the denominator. So √3/√3 in this case. Why again a funny looking 1? √3/√3 just equals 1. When I do that step, 1 times √3 is √3. √3 times √3 is √9, which simplifies down to √3/3 because the square root of 9 is just 3. So this value, we took all of this work to get down to this value is our tangent. So √3/3 is the answer there. Okay, let's keep chugging. So cosecant is going to be 1/y, which will equal 1/1/2. Again, when we divide by a fraction, we multiply by its reciprocal. So you take the top, multiply it by the reciprocal of the denominator, which would be 2/1, or 1 times 2, which is just 2. All right, same thing for our secant. 1/x is our secant value. So 1/x would be 1/√3/2. Again, divide by a fraction, multiply by its reciprocal. So 1 times 2/√3 gives us 2√3. Then we have to multiply in order to rationalize the denominator, which gives us 2√3. And we know that this will be √3 times √3, which is √9. Square root of 9 is 3. So we want to kind of expedite that simplification process, okay, to get 2√3/3. So now for cotangent pi/6. Again, this is the reciprocal of our tangent. So it will be x/y this time, okay? I'm going to try to draw that line so you know that was that work. So that will be, our x value is √3/2, all divided by 1/2. So again, we get to say, all right, that is, keep that first fraction and then change it to multiplication and multiply by this reciprocal. So by 2/1 instead, which will end up being 2 times √3 over 2 times 1, which is 2. 2/2 cancels to leave us with √3. And I'll write √3 up here as our answer as well. Okay, so looking at all the different answers that we have, we have 1/2 √3/2, √3/3, 2 √3/3, and square root 3, that final answer. So as you can tell, a little bit of work can go into these, but it's all things that you've learned in the past, just some multiplication of fractions, division of fractions. and stuff like that. Okay. Okay. So then now we're going to do a different example. This one is evaluate the 6 trig functions for t equals pi. So pi value, the coordinates there are super simple, right? Pi is on one of our axes, so that is -1, 0. So again, x, y. So for our sine value, we should be taking the y value. So super simple. That is just going to be, y value is 0, so it is 0. That's the answer there. The x value, which is cosine, super simple again. Grab that -1 and you're done. Moving on from that part, we can get into tangent. Tangent again is taking y over x. So our y value is 0. Our x value is -1. Oh, sorry, -1. 0 divided by -1 is just 0. Since we do have something in our denominator, it's okay. Cosecant is going to be 1 over y, which is 1 over 0. One of the very first things we said was that your denominator could not be 0. When that happens, it is in fact undefined. Okay, so this one's going to be undefined. For a secant of pi, that's 1 over x, which would be 1 over -1. So that value there is -1. Cotangent pi is x over y, which would be -1 over 0. Again, we're dividing by 0, so this one ends up being undefined. Okay, so this one, whenever we have an axis radian measure, meaning it's just going to be either 0, -1, or +1, super quick, simple stuff, just making sure you understand where it becomes undefined. So for this last one of this kind of example, we are now taking, we're evaluating for a negative radian measure. So yesterday in 4.1, we talked about negative angle measures. If you have a negative angle measure, you will be moving, not counterclockwise, sorry, I don't know why I put counterclockwise. You will be moving clockwise along the unit circle. So let me pull one up really quick. Let me see where I can go find one of my notes. All right. So here's not the most best version of it. Okay, so with going a -√3, again, that's moving clockwise. So generally with the unit circle, you have to consider the fact that we are always moving clockwise or counterclockwise to go figure out these angle measures. So negative would be going the opposite way. So we have to think absolutely backwards. When we have a positive √3, that's our first division line when we're talking about dividing into thirds. So that's the positive measure though. So we are having to move clockwise, which would be going from here now to our first over 3 division line. So this would be the coordinates that we grab. They're going to be the same no matter what. When we're talking about a over 3 divider, you're going to have 1/2 √3 over 2. But it just depends on the negatives. So in this quadrant, okay, in this quadrant, this is quadrant 4, your x values are positive, but your y values are negative. So it will be a positive 1/2 and then negative root 3 over 2. Okay, so that's where we're getting these coordinates from. So now again, let's evaluate for sine of negative pi over 3. That is again just the x value, okay? Or sorry, just the y value. So you just pull that negative root 3 over 2, and that is all. So then moving on for cosine, you are pulling cosine negative pi over 3. It's my x value, so it's just positive 1/2. Oops, sorry. Positive 1/2. And then for tangent, negative pi over 3, that is y over x. So at this point then, we have to take negative root 3 over 2 divided by 1/2. So this will end up getting just a little bit messy, right? We have to take our numerator, negative root 3 over 2, and multiply by the reciprocal of 2 over 1, which will just end up equaling negative 2 root 3 over 2. And 2's cancel to give us negative root 3 as an answer for tangent. All right, now for cosecant negative pi over 3, that is going to be 1 over, here we go, that will be 1 over y. So that is then taking 1 over negative root 3 over 2, which we have to take 1 times 2 over negative root 3, giving us negative 2 over root 3. We have to rationalize the denominator, which will equal negative 2 root 3 over 3. All right, 2 more. Let's go with secant. Secant of negative pi over 3 is going to be 1 over x. So this is 1 over 1/2, making it 1 over 2 times 1, or just 2. Last, cotangent of negative pi over 3 is x over y. So 1/2 over negative root 3 over 2. Okay, we keep the 1/2, multiply by the reciprocal. So 2 over root 3, giving us 2 over 2 root 3, still negative. 2's cancel. We get negative 1 over root 3. You have to rationalize this denominator, which will give us negative root 3 over 3 for that one. Okay, so there are 3 different examples of the exact same problem, just evaluating for the 6 trig functions. Those kind of problems are huge. They are not easy, guys. Getting into chapter 4 and chapter 5, like precalc is really picking it up now. We're not so much just doing a review of chapter or of algebra at this point. We are really going to start picking it up. And this is where, if you're not kind of trying your hardest, asking questions, making sure you're doing the homework, things will get really confusing really fast. So just make sure you're staying up with everything and doing your best to get that homework done and make sure you have a good understanding of everything. So two more kind of concepts I want to talk about. The first one is when we are evaluating for large radian measures. This means it's a radian measure over 2 pi. You can in fact break that up by taking out all the different, this is called 2 pi n, because basically this n stands for how many full laps around the unit circle did you do. So the unit circle is a full 2 pi, right? So we are saying, how many times do I fully go around the unit circle? Do I go around once, twice, 3 times, 4 times? No matter what, I can take all of those full revolutions out. Whatever's left over, if I just evaluate for that, so just sine of t instead of sine of whatever that large version was. So same thing for cosine. If you just take out all the full revolutions and simply evaluate for that little leftover chunk of a radian measure, you will still get that same answer. So I have two examples for you. The first one, I want us to evaluate the following. This is 13 pi over 6. So we want to say, how many full times did I go around the unit circle? So essentially, we have to see how many full 2 pi's can I take out? Let's think about this in kind of like a mixed number sense. So how many times does 6 go into 13 wholly? Right, so nothing like I'm not like going in like, oh, 2.5 times. So I'm going to say, how many times am I going to go into there wholly? 6 can go into 13 twice. So that's representing 2 pi. And then that was 6 times 2 would be 12. So 13 minus 12 is 1, meaning I have 1 pi over 6 left over after taking out that 2 pi. So instead of evaluating for 13 pi over 6, because that's a massive radian measure, I can instead of all of, right, I'm going to evaluate for sine. Instead of evaluating for that, I break it up and I say, all right, let's evaluate for just sine pi over 6, okay? The y value at pi over 6 is 1/2. So it's just simply 1/2. And again, these coordinates are being pulled off the unit circle. So if we go back to unit circle, pi over 6 is right here. Okay, pi over 6 right there. So the y value at pi over 6 is just 1/2 in that coordinate. Next example, negative 7 pi over 4. That's not what I wanted. Nope, that's not the value I wanted, sorry. Let's scratch that one. It's not the example I wanted. Let's do 9 pi over 3. And I'm evaluating for cosine at that value, where theta is 9 pi over 3. So wait, just a second, sorry. I think I'm finding, this is not the right example that I wanted. Just one second, I'm gonna pause this really quick and find the right example. Okay, sorry, I wanted to go grab this. This is the example I want, but I wanted to grab a cleaner unit circle to kind of show this to you on. So the way that we're actually going to count this out too. So for this one, for 9 pi over 3, we want to know how many full revolutions do we do around the unit circle. So we start here always, and we're going to count on every third. So this is 1, 2, 3, move this up, 4, 5, 6. Okay, so let's make a little tally. We went around once already. And now 7, 8, and 9. Okay, so we only made it 1.5 times around. So what this is saying is we landed back on pi. So we went a full 2 pi and then an additional pi. So we have pi plus 2 pi is what we're essentially taking this cosine of. So instead of adding on this additional 2 pi, we're only going to take cosine of pi, and cosine is our x value. At pi, that cosine value is -1 because that's our x value. So it just equals -1, and it's just quick and as quick and simple as that. So, okay, one last thing I want to talk about, and this one I promise is super quick. So we, just like we had even and odd functions when we were talking about linear functions, we also have even and odd functions in trig. So if you don't recall, an even function would be when you input a negative, it outputs a positive. And an odd function would be you input a negative and it outputs a negative, okay? So the odd functions are sine, tangent, cosecant, cotangent, even, cosine, and secant. So if we want to find, or if given, tangent of t is 2/3, find tangent of -t, okay? So tangent is an odd function, meaning you put in a negative and it outputs a negative. So we are currently inputting this negative for the t, so it should output a negative as well. So my t will equal -2/3. Okay, next one, sine of t equals +4/5. Find sine of -t. So again, if you are inputting a negative, you output a negative. So this will become a -4/5. The only time this would change basically is if we had a cosine or secant function. All right, that is it for this video. Thank you very much for watching.